Hey guys, here are your notes on section 4.4, day 2, finding the complex zeros of a polynomial function, okay? Just to review a couple of the functions that we saw from yesterday, the theorem said the zeros to a polynomial function are complex zeros, either real or imaginary numbers, right? So these zeros now, they don't just have to be real, we can find the imaginary ones too. All right, according to the conjugate pairs theorem, imaginary zeros, they come in pairs, right? So if you're gonna have an imaginary zero, like 3i, then you automatically know negative 3i is a zero as well, because the imaginary zeros, they have to come in pairs. Okay. Another theorem, every polynomial function with real coefficients can be uniquely factored over the real numbers into a product of linear factors and or irreducible quadratic factors, right? All right, so basically what this is saying is all of your real number zeros become a linear factor, right? Like if 5 was a zero, a real zero, then x minus 5 was a factor to that polynomial, right? And it's saying that all of your imaginary zeros, that they come in those conjugate pairs, they can become the product that will always be an irreducible quadratic factor. So for example, let's say 2i was a zero, right? An imaginary zero. Then we also know that negative 2i, his conjugate, had to be a zero as well. So then you can write them as those strange looking factors. Well, when you multiply these factors out that have these imaginary zeros in them, they're always going to multiply to the product of an irreducible quadratic, a quadratic function that can't be factored or it can't be reduced, okay? And that makes sense because the reason you got these imaginaries in the first place is because you were working with a quadratic that you couldn't factor, okay? All right, so just remember that. That's important, that they come in pairs and that the product of these zeros can always form a quadratic that won't be reducible, okay? All right, here we go. Look at example 1. They want us to, in example 1, we're going to find the complex zeros of the polynomial function given here, and then we're going to write it in factored form. So when we write it in factored form, we'll write all of our real zeros as those linear factors, and we can write any imaginary zeros, their pairs, become that irreducible quadratic factor that we can write it as, okay? All right, so here we go. So if I'm looking at this one, it doesn't look like any of our factoring techniques are going to work here, right? It's a degree 4 polynomial, so what we know is that a degree 4 polynomial will have 1, 2, 3, 4 zeros, right? Whether they're real or imaginary or repeated, right? It's going to have 4 zeros. All right, so it looks like we're going to have to do our P's and Q's in order to find our zeros. So I'm going to get my list ready. And again, I know you can go right to the graphing calculator, but I'm going to at least make my list first. All right, so P over Q, right? Factors of the constant over factors of that leading coefficient, FCon over FCO. So that means we're going to need factors of 18, which are what? 1, 2, 3, and then we would get 6, 9, and 18 over factors of the constant, which is going to be 3. 1 and 3. Oh, I said constant. I'm sorry. I mean factors of the leading coefficient. All right, so here we go. Let's create our fractions. Plus or minus 1 over 1 is 1. Plus or minus 1 over 3 is 1/3. Plus or minus 2 over 1 is 2. Plus or minus 2 over 3 is 2/3. Plus or minus 3 over 1 is 3. Plus or minus 3 over 3 is 1, guys. So I don't have to repeat that again. I already have him. All right, and then plus or minus 6 over 1 is 6. Plus or minus 6 over 3 is 2. I already have 2, so I don't have to list a repeat. So now we'll go to 9. Plus or minus 9 over 1 is 9. 9 over 3 is 3. I already have 3, so I don't have to list that. Plus or minus 18 over 1 is 18. And then plus or minus 18 over 3 is 6. And I already have 6, so I don't have to list that again. So if this degree 4 polynomial is going to have any real rational zeros, it's a number on this list. Well, instead of us sitting here to test them, I'm just going to flip over to my graphing calculator and see which one works to see if I could narrow it down that way. All right, I just actually am going to show you on Desmos instead. All right, so here I've typed in that equation, and I can see that it looks like it's crossing over at -2, x is -2, and it looks like another one is at 1/3. So that means I could try either one of these to start breaking this degree 4 polynomial down. I'm going to do -2, all right? All right, so -2 should definitely work. We saw that it's definitely a 0 in x-intercept, so I'm going to use -2 to start breaking this degree 4 polynomial down, right? I know one round of synthetic will turn it into a degree 3 polynomial, all right? So even if you wanted to say, right, -2 is definitely an x-intercept or a 0 because we just saw it from the graph, and even if you wanted to list 1/3 because we saw that on the graph, you could. But these last two, maybe they're imaginary, maybe they're irrational, and they're not on this list. So we're going to at least have to start breaking the polynomial down to start finding the least remaining two zeros that we still don't know. All right, so here we go, -2. Let's see, I have x to the fourth, x to the third, x squared, just x, just number. I don't have to fill in any zeros. So my coefficients will be 3, 5, 25, 45, and -18. Now I have to get a remainder of 0 because we've already seen on the graph that it crosses at -2. So this is a 0, which would create a factor, so it should divide evenly in, and I should get a remainder of 0. All right, 3 times -2 is -6. We add, we get -1. That's going to be 2. We add, we get 27. That's going to be -54. We add, we get -9. I get 18. And there it is. There's my remainder of 0. All right, so one round of synthetic just proved that, yes, -2 is one of our zeros, so we can definitely put them on our list. All right, now, after one round of synthetic, this degree 4 polynomial these become the coefficients to a degree 3 polynomial 1 degree less, right? So now I could, knowing that 1/3 was another crossover point, I could take 1/3 and these coefficients and do another round of synthetic and get it down to a quadratic, a degree 2, that I know we could either factor or use the quadratic formula on. But guys, if you're looking at these coefficients, this looks like a degree 3 polynomial that would factor by grouping. So I'm going to put the variables back in, right? 1 degree less, so this will be 3x to the third minus x squared plus 27x and then -9. I'm going to set this equal to 0, and I'm going to solve it like this because it looks like it's going to factor by grouping, and then I don't have to do synthetic again. All right, so if I group the first two and I group the second two, I look for their GCF, it's x squared. That leaves me with 3x minus 1. All right, I have to pull out the leading sign. The GCF is 9, and that's going to leave me with 3x minus 1. So guys, factor by grouping worked. So now I know, let me just move it up. I know one of my factors is going to be 3x minus 1, and I know another factor is going to be x squared plus 9, what I factored out, right? Sorry, my phone's going crazy. All right, so now I could just solve this, set each factor equal to 0. If I set this equal to 0, that's where my 1/3 is going to come from, right? I already knew 1/3 was one of my zeros just by looking at the graph, but now I calculated him. Now I can find my remaining 2 by setting this factor equal to 0. So if I set x squared plus 9 equal to 0, I will get, let me just move it up again. I'm struggling here. All right, I'm going to get x squared equals -9. Take the square root of both sides, and x will equal plus or minus the square root of -9 is going to be plus or minus, I'm not on view here, just bear with me. Technical difficulties here. All right, I'm going to get plus or minus 3i. So now I can fill in that my remaining 2 zeros are going to be, why am I struggling so much? I can't see if this thing is in your way or not. I know it's going to be positive 3i and negative 3i. So now I have found all 4 zeros to my degree 4 polynomial, all right? Now it asks you to write it in factored form. So like I said, all of your real zeros, these 2 zeros, can be written as a linear factor, and then your imaginaries that come in pairs, they can always be written as an irreducible quadratic factor, which, guys, it's this guy right here. This is the irreducible quadratic factor that created those 2 zeros. So when I go to write it in factored form, I'll get f of x equals, I always like to put a in case I need to throw in a leading coefficient. I can write -2 as a linear factor of x plus 2. I could write 1/3 as a linear factor of x minus 1/3. I know we usually don't see it like that, but you are allowed to write it like that. And then you could write these 2 zeros as the irreducible quadratic x squared plus 9. All right, now, if you notice, I need this to multiply back to that leading coefficient there, 3x to the fourth. So right now, x times x squared only gets me back to a 1x to the fourth. I need a 3x to the fourth. So that means I could easily make my leading coefficient a 3, and then 3 times x squared will get me my 3x to the fourth, all right? Or I could say f of x equals A. If I want to write x plus 2, I could rewrite 3x minus 1 as that linear factor 3x minus 1, which looks a little bit more normal. And then your irreducible quadratic factor, x squared plus 9. Now, when I multiply my fronts, x times 3x times x squared, that'll get me my 3x to the fourth. And in that case, you could just let A be 1. You don't need A to be anything because your factors will multiply out to that leading power function 3x to the fourth. All right, either one, they're going to mark correct, okay? Now, I believe if you wrote this as x minus 3i and this as x plus 3i, and you wrote them as linear factors, I believe they want those ones written as that irreducible quadratic, okay? All right, perfect. So either one of these would be correct as your factored form, and then here are your 4 zeros to this degree 4 polynomial. All right, let's try another example. Okay. All right, let's look at example 2. Example 2 says, find the complex zeros of the polynomial function given here, and we want to write it in factored form. So again, I would try to group it, but you're not going to get that common factor, so it doesn't factor by grouping. So we are going to have to use our P's and Q's here. I know we could look at the graphing calculator, but at least to get started. So just take note, this is a degree 3 polynomial. So if this is a degree 3 polynomial, it's going to have 3 zeros, which means 2 of them could be imaginary, but remember, an odd degree has to have at least one real one. All right, so let's make our list of P's and Q's. Factors of the constant over factors of the leading coefficient. So I need factors of 5, 1 and 5, over factors of the leading coefficient 2, 1 and 2. So it's not going to be a very long list of options, plus or minus 1, plus or minus 1/2, plus or minus 5, plus or minus 5/2. Well, let's look at the graph to see which one we want to use. All right, let me turn this one off. This one's graph, it looks like, here's the graph of it. It looks like it only crosses over one time when x is 0.5, 1/2. So it looks like 1/2 is going to be the one we're going to use. And that means since it doesn't cross over again, it means that remaining 2 zeros, they must be imaginary, right? So let's use, we know right now it looks like 1/2 is our guy, is one of our zeros. So let's do 1/2. I can use 1/2 to break this degree 3 polynomial down into a degree 2, which we could then at least factor. Or use the quadratic formula. All right, so I have an x cubed, x squared, just x, just numbers, so I don't need to fill in any zeros as my coefficients, 2, 3, 8, and -5. Bring down the 2. Now again, since we saw that it crossed, it definitely should get a remainder of 0. It should divide evenly in. So I bring down the 2. I get 1, 4, 2, 10, 5, and then there's my remainder of 0. So now these become the coefficients to a degree 2 polynomial, right? After one round of synthetic, this degree 3 polynomial will leave us with the coefficients to a degree 2 polynomial. So that's going to be a 2x squared, a 4x, and a plus 10. So now I can take this degree 2 equation and I can solve it. So I can set it equal to 0 and find the remaining 2 zeros. Now I'm going to factor out a 2, just divide it out. That's going to leave me with x squared plus 2x plus 5, right? All right, so now I can find my last 2 zeros by, it's not going to factor, so we're going to use the quadratic formula. So x will equal -2 plus or minus the square root of 2 squared minus 4 times 1 times 5 all over 2 times 1. So x will equal -2 plus or minus. That's going to be what? 4 minus 20. That's going to be -16. The square root of -16 is 4i. All right, all over 2. Both of these divide by 2, so x will equal -1 plus or minus 2i. So my remaining 2 zeros are imaginary. One of them is -1 plus 2i, and one of them is -1 minus 2i. So I found all 3 zeros. Now I have to write f in factored form. So my real zeros can become that linear factor. Your imaginary zeros that came in a pair, they can go to that irreducible quadratic, which was, guys, right here. This is the irreducible quadratic function that those would multiply back to. All right, so when I go to write it as factors, I'm going to say f of x equals, I'm going to put a leading coefficient there in case I have to fill something in. I could write my real 0, 1/2 as x minus 1/2 times, they're going to be that irreducible quadratic right there, x squared plus 2x plus 5. Now, the only reason I wouldn't use this one is because this one to me is reducible. I could reduce it by a factor of 2. This is the irreducible quadratic that got those 2 zeros, okay? So now if you look here, my fronts will multiply back out x times x squared to a 1x to the third. I need it to multiply back out to a 2x to the third. So in this case, I'd have to make my leading coefficient 2, so that 2 times x squared gets me that leading power function, 2x to the third. All right, but if I wanted to write it like this, f of x equals a times, if I wanted to write 1/2 as 2x minus 1, right? Because that would definitely get me a factor, a 0 of 1/2. And then my irreducible quadratic, x squared plus 2x plus 5. Now, the way I've written it here, 2x times x squared will get you that 2x to the third, that leading power function. So in this case, you could let a just be 1, or you don't need anything in front, okay? Either one of them would be completely correct on your homework. All right, so that's how we can, again, find our zeros using the graphing calculator or Desmos to help find the one that would get us that remainder of 0. All right, look here. Couple more examples and we are good to go. Look at this one. Example 3 says, use the given 0 to find the remaining zeros of each function. So in this case, guys, they've given you a polynomial function and then they've told you one of its zeros. So they must have done that for a reason. If I want to look at his graph, even if I was to make up my P's and Q's, right? We know this is a degree 4 polynomial, so I know it has to have 1, 2, 3, 4 real, not real, it has to have 4 zeros, right? So technically, if you think about it, the imaginary ones come in pairs, right? So an even degree could have all imaginary zeros. If that's the case, then looking at its graph won't help you because it wouldn't cross over the x-axis because imaginary zeros don't make x-intercepts. So maybe they told us that 0 for a reason to help us, right? Let's see. Let's look at its graph. Well, first of all, I apologize. I'm going to find my list of possible zeros. So I'm going to do my p's over q's, my factors of the constant over the factors of my leading coefficient, right? That means I would get factors of 12 over factors of 1. So 1, 2, 3, 4, 6, 12 over 1, right? So technically all of my possible rational zeros are going to be plus or minus all of these whole numbers, right? Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4. Now, if I looked at the graph to see which one I'd want to try first to start breaking this degree 4 polynomial down, if I looked at the graph, let me turn this one off, this one on, it looks like, according to the graph, let me zoom in a little bit. All right, it looks like it's crossing over at decimals. This one is negative 0.646, and this one is 4.646. None of our possible lists, none of our possible zeros were fractions. So that means that those decimals must be irrational zeros. And this list can only find the rational zeros. So this list is going to do nothing for us. Looking at the graph, none of them are going to work. None of them are going to get us that remainder of 0 because none of these were the actual zeros on that graph. So they must have given this to us for a reason, knowing that maybe these wouldn't work, right? So we know 2i is one of our 4 zeros, which then we know if 2i is a 0, his pair, his conjugate, negative 2i, is also a 0, right? So the other 2 zeros must be irrationals. They're not on this list. So I'm going to need to start breaking this polynomial down to find the last 2 zeros. So guys, think about what they told us. We know that these pairs, these imaginary zeros, they're always going to give us that irreducible quadratic factor. I need that factor. So I'm going to write them as zeros, as factors, as weird as that's going to look. I'm going to write this 2i as a factor of x minus 2i. And I'm going to write negative 2i as x plus 2i, right? That's what they would look like as factors. This is always going to get you an irreducible quadratic. So I'm going to multiply it out, FOIL it out, and get me that irreducible quadratic. All right? So now I'm going to get x squared plus 2ix minus 2ix minus 4i squared. Well, they'll cancel, and that'll leave me with x squared minus 4i squared is negative 4 times negative 1. That's plus 4. So guys, here's that irreducible quadratic factor that those two imaginary zeros will get me. So think about it. If this is a factor, right, because he came from those zeros, what do we know factors will do to that polynomial? We know they will divide evenly in. So now I know I can divide this polynomial into that one and start breaking it down into a smaller polynomial. If I divide this one in, it's going to get me a degree 2 polynomial into a degree 4 polynomial. It's going to get me, my answer will be a degree 2 polynomial. And if I can get to a degree 2, a quadratic, I could factor it or use the quadratic formula, right? So we're going to take this quadratic factor and we're going to divide it in. The problem is you can't use synthetic division when you divide by a quadratic factor. You have to long divide this quadratic factor in to that polynomial. All right, so I'm going to take x squared plus 4 and I'm going to long divide it in to this polynomial. So hopefully you remember your long division. All right, I still need to look for missing terms. X to the 4th, x cubed, x squared, just x, just number. I don't need to fill any zeros in because nothing's missing. So x to the 4th minus 4x to the 3rd plus x squared minus 16x minus 12. All right, here we go. We're going to long divide. So what I do is I take the first term of this polynomial and I try and divide it into the first term of this polynomial. So how many times does x squared go into x to the 4th? Or x squared times what gets you an x to the 4th? An x squared. So above your x squareds, give yourself an x squared. We're going to kind of placehold here. That's your division step. Now we multiply it in. So x squared times x to the 4th x squared times x squared is x to the 4th. You want these two terms to match because when I go to subtract in the next long division step, I want these two to cancel. So I always want whatever is here, I want this to match it. All right, and then what's x squared times positive 4? That's positive 4x squared, right? So you want to line them up. Then we're going to subtract. But you got to be careful when you subtract. You got to pick up that subtraction every single time. So x to the 4th, subtract x to the 4th. They cancel out. They're gone. That's what you want to happen. Negative 4x to the 3rd, subtract nothing, is going to be negative 4x to the 3rd. And then x squared, subtract 4x squared. It's kind of like multiplying a negative times a positive would be negative. So x squared minus 4x squared is going to be negative 3x squared. All right, and then we bring down negative 16x minus 12, and we're going to do it all over again. All right, so now we divide. How many times does x squared go into negative 4x to the 3rd? Or x squared times what gets you negative 4x to the 3rd? A negative 4x. So now above your x's, we put it there, negative 4x. All right, now we multiply. What's negative 4x times x squared? Negative 4x to the 3rd. Negative 4x times positive 4 is negative 16x. So line them up, and now we subtract, but pick up that subtraction every time. Negative 4x to the 3rd, subtract negative 4, that turns to a plus, they cancel. Negative 3x squared minus nothing is going to be negative 3x squared. Negative 16x, subtract negative 16, a minus turns to a positive, and then they cancel. All right, and then we bring down we don't bring down. Negative 12, subtract nothing is negative 12. All right, there's nothing left to bring down, so we do it one more time. All right, what do we got? How many times does x squared go into negative 3x squared? Well, negative 3 times, right? X squared times what gets you negative 3x squared? Negative 3. So above your just numbers, you put your negative 3. All right, now we multiply. Negative 3x squared, negative 3 times x squared is negative 3x squared. Negative 3 times 4 is negative 12. And now we subtract. Negative 3x squared, subtract negative 3 turns to a plus, so now they cancel. Negative 12, subtract negative 12, negative turns to plus, and now they cancel. Nothing left to bring down. My remainder is 0. So now I am left with a degree 2 polynomial. This times this gets you him, but I can use this next polynomial to find the last two zeros. So, take this quadratic, x squared minus 4x minus 3, set it equal to 0, and get your last two zeros. All right, I'd love to say it's going to factor, but the reason that these are irrational, that they weren't whole numbers on this list, was probably because this didn't factor. All right, and it's true. Nothing's going to multiply to negative 3 that adds up to negative 4. So we're going to use the quadratic formula. X equals 4 plus or minus the square root of negative 4 squared minus 4 times 1 times negative 3 all over 2 times 1. So x equals 4 plus or minus. This is going to be the square root of who? That's going to be 16 and then plus 12. That's going to be 28, right? So the square root of 28 reduces to root 4 root 7 to root 7. So plus or minus 2 root 7 all over 2. So you see, it's an irrational zeros, and they come in pairs as well. So this irrational zero, I never would have gotten from my rational zeros theorem. All right, so these both divide by 2, so x will equal 4 divided by 2 is 2, plus or minus 2 root 7 divided by 2 is root 7. So those are your remaining 2 zeros. So one of them is going to be 2 plus root 7, and the other one is going to be 2 minus root 7, and that's going to be that 0.646 and that 4.646, whatever we saw on the Desmos before. All right, so again, if you know an imaginary zero, you automatically know a second one. They will always multiply to an irreducible quadratic, and then you can take that irreducible quadratic and divide it into that original polynomial and start breaking it down to get an easier polynomial to solve. All right, let's try one more of those, and then I'm going to let you guys go. All right, look at the last one. All right, same thing. It should say find the complex zeros of the polynomial function, all right, and given one of its zeros. So again, they've given us one of its zeros. So I'd like to think they've given it to us because we're going to need it. Sometimes they'll give it to you even if it has a real rational zero, but again, I'd like to think here it's probably a reason they've given it to us. Let's see. Let me see its graph. So if I look at its graph, look at that. See this? Look, it's a degree 4 polynomial. Let me come back. It's a degree 4 polynomial, right? So I know it's going to have 1, 2, 3, 4 zeros, whether they be real or imaginary. But remember, an even degree polynomial, it could have 2 imaginary and 2 imaginary. It doesn't have to have any real zeros. So if I look at the graph to try and figure out, my P's and Q's, who should I try first? Well, guys, if I look here, it doesn't look like it's crossing over the x-axis. Where's the graph, right? It's nowhere. Let me zoom out a little bit. Oh, there it is up there. So guys, there's the graph. I don't think it's crossing over, so we'd be wasting our time to use our P's and Q's because it doesn't look like it has a real number 0 that it's going to cross over the x-axis at. So this looks like a degree 4 polynomial that is entirely above the x-axis, which means all 4 of its zeros are imaginary. So that's probably why they gave us one of them as a hint, because using P's and Q's here would get us nowhere. All right, so if I know 3 minus 2i is a 0, then I automatically know his conjugate 3 plus 2i is a 0. So now the other two look like they're going to be imaginary as well. So I'm going to take these two, I'm going to write them as factors, and then I'm going to multiply those factors together to get me an irreducible quadratic that I could divide into this one. All right, so x minus 3 minus 2i is a 0 or a factor, and then x minus 3 plus 2i, right? I can write them as factors. I'm going to distribute my negative. I get x minus 3 plus 2i, and then x minus 3 minus 2i, all right? So now, as weird as those factors are, they are factors of this polynomial. So I'm going to multiply them together, and they're going to become an irreducible quadratic, all right? Now, if you remember yesterday, I showed you guys a trick. If you think of x minus 3 as a, plus, and you think of 2i as b, right? So this is a, and then this is minus, this is b. A plus b times a minus b will always multiply to a squared minus b squared, right? The difference of two squares always factors to a plus b and a minus b. So now I know this will multiply out to x minus 3 was a squared, minus b was 2i squared. And now I could just do this, and I could use my foiling tricks. So this will FOIL to x squared minus 6x plus 9, and then minus, that'll be 4i squared. Well, that's going to be minus what? Negative 4, which will be plus 4. So that's actually going to become x squared minus 6x plus 13. So this is the irreducible quadratic that these two zeros made. All right. Now, again, if you don't want to do my trick, then all you have to do is distribute x, distribute negative 3, negative 3, negative 3, and then distribute 2i, 2i, and 2i. I'd rather do this. It's much quicker, and I feel like you're likely to make less mistakes because you won't have many terms to work with. All right, so let's take this irreducible quadratic. Let's divide it in. If I divide a quadratic into a degree 4, I'll be left with another quadratic that I could then work with. All right, so how many times, let's see, does x squared minus 6x plus 13 go into this polynomial? Now again, x to the fourth, x to the third, x squared, just x, just number. It's not missing any terms, so I won't have to fill any zeros in. All right, x to the fourth, 6x to the third, plus 15x squared minus 12x plus 26. Now again, because I've created this factor from his zeros, it's got to divide evenly in. So if you don't get a remainder of 0, you did something wrong. This, or you created the wrong factor. You didn't multiply it out correctly. Okay? All right, here we go. All right, so x squared goes into x to the fourth how many times? X squared times, right? So x squared times x squared gets me that x to the fourth. All right, so now we multiply it in. X squared times x squared is x to the fourth, right? I want these to match because I want them to cancel. X squared times negative 6x is negative 6x to the third. Now, this one doesn't have to match. It just happens to match here. X squared times 13 is 13x squared. All right, now we subtract, but we're going to pick up that subtraction the whole time. X to the fourth, subtract x to the fourth, they cancel. Negative 6x to the third, subtract negative 6x, negative negative turns to a plus, and then they cancel. And then 15x squared, subtract 13x squared is 2x squared. So be careful. It looks like you should get 28, right? But you don't. Pick up the subtraction. All right, and then bring everything down. Minus 12x plus 26. Let's do it again. All right, how many times does x squared go into 2x squared? Or x squared times what gets you 2x squared? A 2. So now to placehold, put it above your just numbers, right? All right, so now we multiply. 2 times x squared is 2x squared. 2 times negative 6x is negative 12x. 2 times 13 is 26x. We subtract. 2 take away 2x squared, they cancel. Negative 12x subtract negative 12 turns to plus, they cancel. 26 subtract 26, they cancel, and I'm left with 0, right? Which I should have, because I knew this was a factor, all right, provided that I multiplied it out correctly. All right, so that leaves you with this degree 2, this quadratic that we could then set equal to 0 and solve for our remaining 2 zeros. All right, so at least it's an easy one. X squared plus 2, set it equal to 0. I'm going to minus 2. I'm going to take the square root, and x equals plus or minus I root 2. So now I know positive I root 2 is my third 0, and negative I root 2 is my fourth 0 to this degree 4 polynomial function. Okay? All right, guys, that was a lot. Reach out to me if you have any questions, and I'd be more than happy to help you.